everybody. Thank you so much for joining us for a perfect brew teaching equilibrium with tea and Vernier sensors. We are so excited to dive into this super exciting kind of food chem, green chemistry experiment with you all. As you get settled in, I would love to direct you to the bottom of your Zoom window. At the bottom there, you'll see a little chat bubble icon. That is where you can access all of the chats that we're sending today. That's how you can ask questions. So go ahead and click that and it'll pop up your webinar chat. And at the bottom left, you'll see a little to section. Make sure that to section is set to everyone. That helps us in two ways. One, it helps your fellow educators figure out what other people are wondering, kind of builds that conversation, but it also helps us look like we're not talking to ourselves. So please make sure your questions are set to everyone. With that being said, go ahead and type in that webinar chat. Well, we're talking about tea today. Go ahead and let me know what your favorite flavor, variety, etc. of tea is. I'm a chai tea girl, which I know just means tea, but you know what I mean. We've got a peppermint person.
I am also not a tea drinker, so yeah.
Oh, good to
I'm glad
know.
I'm not alone.
Solidarity in the chat.
Yes.
Oh, yeah, we've got another non-tea
Mm.
drinker.
Mm-hmm.
Jennifer says peach. Kevin says green tea and Irish breakfast tea. Yep. Oh,
Another
another Irish
chai.
breakfast. Yep, there we
Mm-hmm.
go.
Mm-hmm.
Strawberry, cinnamon spice. Yum.
Ooh, fruit infusions, yeah.
Yum. Peach mango green tea. Delicious.
Ready for
Jasmine.
summer with that one.
I know. These all sound amazing. I'm like, maybe I'm dehydrated. I need to. Ooh, pumpkin spice rooibos tea. I might say that right. Awesome. All right. Well, we're a minute past the hour, and I know we have a lot to cover, so I do just want to hop into some housekeeping items really quickly. Most importantly, you will get a recording of today's webinar. It usually takes us about 3 to 5 business days to get that edited and posted. Once it's live, it'll be both on our website and our YouTube channel. Keep an eye out for an email from us. We're also going to email the recording to you. In that email, you will also get a resources folder. In that folder is today's presentation if you want to follow along. I also have a certificate of attendance in there. I'm going to drop that link in the chat as soon as I'm done talking here. We want to answer your questions today. So please put your questions in the chat right where you were telling me about your favorite flavors of tea. We're going to try to keep on top of it. If I see anything that's super timely, I'll unmute myself and ask Melissa. Otherwise, we'll kind of filter through your questions as we get to them. If you ask a question and we just happen to miss it, please email us. You can reach us at chemistry@vernier.com. With that being said, I'll pass you off to today's presenter, and thank you again for joining us.
Hi, everyone. I am Dr. Melissa Hill, and I'm the Director of Chemistry here at Vernier. I just want to reiterate what Dylan said about please put your questions and comments in the chat box today. And definitely go to that resources folder that she just linked. It has the slide deck, which has lots of helpful links and stuff in it. This experiment is like hot off the presses, brand new. And so it's not written up yet officially, and I would love to get your feedback. So also give me your feedback in the chat or shoot that email to chemistry@vernier.com because it's not even published yet. We're going to be doing this workshop at ChemEd later in the summer, and it's actually based on one of Beyond Benign's experiments. So we're kind of doing a little joint experiment workshop together here, but I'll talk more about that later. So today's focus is we're going to be all things equilibrium. We're going to do a very visually engaging green chemistry, safe, student-led experiment using butterfly PT. And I know when I was teaching in the classroom, equilibrium in particular is a very difficult topic for students to understand. And it's a difficult topic to articulate and teach. So hopefully this experiment will help you with some of those concepts in a way that is a little bit more exciting and engaging than some of the previous ways we've done equilibrium. And it's going to really touch on the concept of dynamic versus not equilibrium, not being static, Le Chatelier's principle, and pKa. So we're going to be using 2 Vernier sensors today. You can really use 3 Vernier sensors with this experiment, a temperature probe, especially for all those of you that are not tea drinkers. And don't have a really nice kettle. Like I have some coworkers that are really big into tea and they have these really pretty fancy kettles that like keep the temperature. No, I'm just gonna use a hot plate. A temperature probe, pH, and a spectrometer. So let's dive right in. If you've been teaching the last few years and your students have a smart device and access to the internet, they may look at videos every once in a while. Can't imagine. And a viral video went around a couple of years ago that was butterfly PT and putting lemon in it, and that it made this beautiful color change. And I cited sources here, but you can just Google it and see all these beautiful videos. I'll show this one real quick, and they just show the lemon and it turns from blue to purple in a really pretty, beautiful way. And whoa, hang on, let me make sure everything's stopped. Okay, sorry about that. So this color change means that something is happening at the molecular level, right? But what is that? And what could have caused that change? The lemon juice. Let's think about what lemon juice is and what it could be contributing. And voila, you have yourself an equilibrium experiment. So the first part of this experiment is really just investigating that dynamic, making sure students understand that equilibrium is dynamic, because it's a really common misconception that students think, well, the color changed, right? It went from blue to pink, and it's not changing anymore, so the reaction's over. Nothing's happening. Equilibrium means that nothing's happening anymore, and that is definitely not the case. It's not just a more acidic or more basic solution. Equilibrium is dynamic, and molecules are continuing to react even at equilibrium. And stresses like pH change, in the case of this example, will cause that system to shift. And tea has these molecules called polyphenols, and they, at different pHs, they have different molecular structures, and those have different colors. And we're going to get into that in part 2. But part 1 is really just looking at this acid-base immediate reversible color shift. Okay, so into some data. First off, there is some preparation that you do need to do before class. Tea, we need to brew it and make sure it's room temperature. So I did about 2 grams of these butterfly tea leaves.
And we have a
And
question in the chat.
yes.
Where did you source your butterfly tea leaves?
Well, again, there's a lot of tea nerds at that I have as coworkers. So one of them gave me some. But if you do a quick Google search, there's a ton on Amazon available. A lot of tea stores have them. So really any place they don't come in like the little nice bags like black tea or something like that you can just get at the grocery store. At least I haven't seen them. So you would probably have to go to like a little bit of a nicer store that might specialize in tea, but Amazon had a bunch. So. And that's why I was just about to say, I weighed out 2 grams for 300 milliliters of water, but that will vary probably quite a bit based on where you source your leaves, how potent they are. things like that. And so I got them just as leaves and put them in cheesecloth. And you can see I took some pictures here. Heated some water between 85 and 90 degrees Celsius. That part is important. That is the topic of another experiment, but make sure it is between 85 and 90 degrees. Steep it for about 2 minutes. You want it to be pretty dark. So this is it. Now, here, let me get this, my handy dandy white paper here. So that is the brewed tea cooled to room temperature. And I have poured 8 milliliters of it in 2 of my test tubes here. So you can see at 8 milliliters, it's a nice blue color. I do want to verify also before I give it to the students that the absorbance in the 500 to 700, the 2 peaks that you'll see in the visible range are at about an absorbance of 1. That's pretty important for the second part to just keep some consistency in the peak heights. We don't want students to get distracted with that. So we want them to have a nice color to them, and the best way to verify that is with absorbance spectroscopy. So once we've brewed it, it's cooled to room temperature. Now we are going to test some pH of the different samples that we have. And I recommend a few different samples, and I have them out here. Lemon juice, of course, because that's kind of in the original viral video. Baking soda is also a very safe, student-friendly. You could just give your students these solutions and tell them to go. You could do this as a very inquiry-style experiment in that way. And you want to have at least one very acidic compound and one very basic. So I recommend lemon juice and baking soda as the 2 go-tos. And then here I also kind of looked around what was in the building. I have some vinegar, I have some detergent, and I have some Sprite, 7-Up, soda pop. Okay, so then we are going to connect our pH probe. And for data collection today, I am going to be collecting from my pH probe kind of at the same time as I'm going to be collecting data from my spectrometer. So I want to use the progressive web app of graphical analysis. And for those of you who aren't familiar with that, how you access it, I should just do it fresh here, is you just open Google Chrome and Chrome web browser and start typing in graphicalanalysis.app into the URL field there. And now I have access to graphical analysis. This is, if you're using Chromebooks in your classroom, this is the best way to access graphical analysis now. You can do this on Windows, Mac, and then now I can use the installed spectral analysis, but we also have spectral analysis as a progressive web app. So you could do both of them as progressive web apps if you wanted to. We are also going to use Graphical Analysis Pro features today. So there is a free version of Graphical Analysis, and you can do this experiment with the free version. It'll just look a little bit different, and I'll point out those things when we get to it. But Graphical Analysis Pro makes it a little bit prettier. So there is a free license key that we're giving away today. It'll be good for 2 weeks. So make sure you grab that and activate it and use the Graphical Analysis Pro for a little bit. How you activate it is you type it into this field here and press submit. And if you want to give it to your students as well, you just have them do the exact same thing. And that key is in the slide deck, and I think Dylan is going to put it in the chat in case you want to copy and paste it. And now I'm going to connect my pH probe. So you can do this experiment with any of our pH probes, really with any pH probe. But today I am going to be doing it with our TRIS compatible flat pH probe. And I'm going to tell you why. With the progressive web app, you have to do this additional step of saying wireless. And I am going to pair it to the bar. I look at the back where there's a barcode, and there's a little number here. And that is the number that I want to identify in my list of GoDirect sensors. I happen to have paired with this one a little bit earlier, so it already knows which one I want to pair to. So I'm going to say pair. Oops, let me try that again. I took too long. Okay. And then it says pH, and we're all ready to go. So first, before I start talking about why I wanted why I wanted the flat one, I'm going to switch my data collection settings because we're going to measure the pH of multiple different solutions. So I don't want time-based data. I want event-based data. And for those of you that didn't see that, I click this little mode button down here, the data collection settings button. I change the mode from time-based, to event-based. And my event name is going to be the chemical. If, however, you're doing this with the free version, you would just use selected events, and that numbers the data that you take, and then you would just write down in your lab notebook what each test tube number corresponded to the chemical that you added. But I can actually write it in with Graphical Analysis Pro, so I'm going to do that. All righty, so now for the pretty part. So first I'm going to do lemon juice because that was kind of the starter of this whole experiment. And I'm just going to grab some lemon juice here. And again, I measured out 8 milliliters of my tea to put into the test tubes. And now I want to measure 2 milliliters of lemon juice to add to just keep the volumes fairly equal because I want to compare all these with spectroscopy later. And this is the pretty part. We add the lemon juice. And look, YouTube didn't lie. I get very pretty pink data or pink solution there after mixing my butterfly tea with lemon juice. I want to make sure I rinse everything really well because you can get cross-contamination pretty easily. And then the other one I'm going to show is baking soda, and you can just put a little scoop in there, but again, I'm trying to keep volumes consistent, so I just made a little saturated solution here of baking soda. And again, I'm going to put 2 milliliters. And then I pour that in here. And I get a very different green color. So that changed colors. And I did it for all my other solutions, my 7-Up, my vinegar, and my detergent. And now I have a pretty rainbow of butterfly tea. Very pretty. Very, very pretty lab. I have to say so myself. And so what we first want to do is measure the pH of all of these solutions. So I'm going to go through and do that. And my first one here is my control. So when I brewed the tea and let it cool to room temperature, the other thing I want to do is make a bigger meter there so you can see it a little bit better. And I added 2 milliliters of water to this one to make sure, again, that they're all about 10 milliliters. and I press collect. Nothing happens until I press the keep button. And now it's going to ask what chemical I have, and this one is my T, and it is my control. And so because I'm using Graphical Analysis Pro, I can do categorical data, which just allows me to enter words and converts it to a bar graph automatically for me. So it looks a little bit better. All right, and now I'm going to go through and do this for all of my samples. This next one was lemon juice. So the reason that I like using the flat pH probe for this experiment is for a few reasons. First, I have just had a tendency to recommend the flat for a while because it doesn't have an exposed bulb, so it's less likely for students to break it. The other reason I like it for this experiment is because you're working with a lot of household items, and there's a lot of extra stuff in household items. And the fact that this one is a double junction, one gives you a more stable result faster, and it helps the longevity of your pH probe. So it will keep it working better, longer, and that's always a good thing. So that last one was vinegar, and as you would expect, it would continue to be acidic, but it's slightly less acidic. This one here is the baking soda. And then I mixed up just some detergent. If you are just giving them kind of an array of chemicals to play around with, I would try and keep them as limited in color as possible. So that's why I picked Sprite instead of, Coke, or some people want to try and do orange juice, and you can, but it just complicates your absorbance spectra when you get there. All right, and here is my last one, and this is going to be T plus 7-Up. All right, and there I have all my pH values all measured. And now let's see. So we got all that data, and students should take away from this that there were, immediate reversible. I thought about showing the reverse, but remember, we're working with baking soda here. So baking soda and acid. So you might want to either do that as a demo or make sure you have a lot of Tupperware dishes or things for the volcano to go over if you want to show students that reversibility, because it will work well with this experiment. Something else you can do to really emphasize the acid-base immediate changes is have them measure the pH of the solution first. So I thought that was a really good way to bring home, because maybe your students don't know that lemon juice is an acid or baking soda is a base, or don't remember it. I know you taught it to them a while ago, but they need a refresher. So you can have them directly measure the pH of it first, and then measure the pH of the tea combined with it to really solidify the idea of the acid seeing this immediate shift. And that this is all quantifiable, right? So that's kind of the first part, is just showing that Le Chatelier's principle, kind of that basic idea, that equilibrium is constantly moving. But now we want to combine that with the actual, a little bit deeper chemistry and the common issues students have understanding pKa's. And we were just looking at the recent AP Chem exam and what the chief editor said, students didn't do so well on, and equilibrium is always one of the top questions that they don't do so hot on, and where their knowledge gaps are around that. And students typically think, pKa is just a number. It only matters when, like, I'm using a formula, that they really don't understand that pKa is something measurable that you can observe with your eyeball in this case. So we want to drive that home since we have a bunch of solutions that are a bunch of different pH values, and all of them have a measurable, your eyeball absorbance spectrometer quantity associated with that pH. We can hone in on a pKa. For background, I briefly mentioned the polyphenol, and I don't know if these are kind of tiny, these chemical structures, but definitely go to the slide deck and look in on them. This is the red cation. These are the ones that would be in butterfly tea. And this is the blue one where the pH equals your pKa, which is the point that we want to find. So we can find that pKa. And then green means that you have gone above the pKa. And we want to find in the absorbance spectra the crossover point so that we can estimate the pKa. So that's where we're going. And you can do this with any of our spectrometers. You can even kind of do it with the colorimeter. It's not going to be exactly the same, but you'll see that the peaks we are looking at aligns pretty well with the colorimeter LEDs. So you can modify the experiment for the colorimeter. I'm going to be showing it off with the SpectraVis Plus. I have done it with the UV Vis, and it's actually kind of interesting because you get that additional UV peak for the very basic solution. So it's actually kind of interesting. But again, another experiment or another extension. And let's get that data going. Okay, so we're going to be taking data with the SpectraVis Plus, like I said, in spectral analysis. I have already connected and warmed up my spectrometer. So I have let it sitting here in the calibration screen. That's the best way to get a really nice flat calibration. And I'll press finish calibration. I'm just doing absorbance versus wavelength mode, so super basic. We just want spectra. And finish calibrating. All right, so we're all ready to go. I always like to do a warm fuzzy and make sure that my water is indeed a flat line, and it is. And so I've already poured these into cuvettes, but you just do, a mil or two in your cuvette. Make sure they're wiped pretty clean, and put it in the spectrometer so that the clear sides are aligned with the white triangle and the detector light there. And this first one I put in is the, let me actually look back at my lemon juice sample, which is a pH of 2.88. So I'm going to go over here and I'm going to stop that. And now, before I forget what sample it is, I'm going to change the name of this sample. And I can do that two different ways. I can do it right here, which is my preferred way, clicking on the y-axis label and clicking on the little pencil. And then I'm going to say pH 2.88, lemon juice. And that will rename it. All right. And I'm going to do that for all of my samples. This next one is the vinegar. All right. And we got some changes going on. And the vinegar sample was 3.19. Okay. And my next one here is this one is the 7-Up. Ooh, isn't that interesting? Where does everyone think I'm going with this? Anyone have any ideas with the spectra? How are we going to figure out the pKa of this sample? Ooh, yes, that is where I am going with this. There is going to be a gradual change between the absorbance of the weak acid and its conjugate base. And we want to find where that spectral crossover is. And when those two species are closest in their peak heights, that is where we will estimate the pKa. And I don't want to give the impression that this is a super quantitative lab, because it isn't. If you want to have your students really delve into it, you really need a two species system, and this is technically a 3. So the math gets really complicated really quickly. And we're really just trying to get students to understand the connection between the color change, the molecular change, and seeing that as equilibrium as pKa. But I mean, it's pretty cool. Like, I feel like it really clicks for students when they see one peak go away and one peak come in. This one is the one I was saying looks really cool with the UV vis, because this peak, gets all cut off over here. So if you do have a UV vis, you could do a demo or something like that. But right now it's just in the way of my observations. So I'm going to change my scaling here, and I'm going to set it to manual scaling, because otherwise it'll just keep rescaling. Okay, and so that last one right there, which came in, oh, I should probably just turn on the graph legend. That last one that came in super, just all peak in the 600s here, was my baking soda sample, which was 8.53. So I got to rename that one. So otherwise, I will lose track. And then my last sample here is detergent. Oop, that went above my manual scaling. Let's adjust that. And that pH was 8.37. Oh, I might have had those backwards. Well, they're close enough. It's probably okay. pH 8.37, and that was detergent. Okay. So super cool, right? You can kind of start to guess that one of the species involved in the equilibrium has an absorbance here at 567, 568, and the other one probably has one here at like 615 or so. And you can see that one, when it was very acidic, had the majority of its peak was over here in that 560. And then when it became very basic, the majority of it was over here in the 620. And the one that shows them in the closest height proportion was actually my just with water, so my control sample, which was a pH of 5.25. And the pKa of the polyphenol in butterfly tea happens between 4.5 and 5.5. And so we're right in there with our pKa at that, the pH at the equilibrium point. So a pretty good approximation, right? So that just kind of describes that. And you can, again, show the arrows, but as the students like put it in, I just think it really clicks for them when they see the absorbance come in and come out. And yeah, so like I said, they should be able to walk away with the fact that the absorbance spectra are showing these molecular changes that are because of the protonation states. And that it is really tied to chemical structure. And I was hoping, I kind of ran out of time, but we do have this really cool feature in spectral analysis where you can sit on, right now, most of you are probably familiar with, if you've done Beer's law and spectral analysis, you can sit on one wavelength, but now you can sit on multiple wavelengths, and you can pick both of these peak heights to monitor versus pH. And where the two lines cross would also be your pKa. So that, explore that. I got a crude estimate, and it came out to be about 6, and I didn't really like that value too much. So I'm going to keep working on it. So if you figure it out or get some really good results, let me know. And yeah, like I said, this is hot off the presses for those of you who came in late. This experiment hasn't even been written up yet. So I would love to hear any and all feedback. Some of you may be saying, well, that wasn't very quantitative and you could do it with bromothymol blue, or I've been doing it with iron thiocyanate forever and it's super quantitative. You get an ice table and everything. Yes, that is all true. And all of those are great ways to illustrate to students and have students get a hands-on perspective with equilibrium. However, some of them are pretty toxic and pretty nasty. Some of them are pretty expensive chemicals. They're expensive waste disposal. And you don't want students, you like have to have students like really tell them very specifically like concentrations and things, because you don't want them to just play around with the chemicals. So I really like this one for that. I think it's really excellent at visualizing stuff. So if you do that cobalt chloride one that is also beautiful and brilliant colors, you might want to consider, switching to this one, just because that one is so toxic. And yeah, it doesn't have the same types of quantitative as the iron thiocyanate or even the bromothymol blue, but it is a little bit, well, it's a lot safer for you and your students. And it lends itself more to student-led and inquiry stuff. So pick the right one for you, for your class, You can change it up. We're always looking for new ideas. We do have the iron thiocyanate lab written up in advanced chemistry with Vernier. The bromothiamyl blue lab, which is just a 2-species system, so you can get a lot more quantitative with it. I did in a previous webinar, so check that out. And then today, I put some sample data in that resource folder, and there are steps in the slide deck, so don't forget that. But this experiment in particular, it really highlights green chemistry. And if you've been following us for about the past year, we're really releasing a lot more green chemistry resources, green chemistry experiments. So this is another one we're going to add to that collection. And again, like I said, we've been working with Beyond Benign on this. And this one highlights, in particular, just like the safer chemicals, safer solvents, all of it can go down the drain. And not only that, but it's hopefully you're pointing out throughout the experiment, like how this is safer and why this is more important to do instead of cobalt chloride. And so that's a lot of what our experimental write-ups around green chemistry try and focus on, is not just the fact that, yes, now we use food coloring in our labs instead of nickel sulfate. It's actually like telling the students about why we're doing that and why those things are important. So yeah, we have more green chemistry resources. Go to the website. We did a webinar on our titrations and on our electrolysis, so check those out. 2 of them are published on the GCTLC. If you are a follower there in that community, that is a great community if you're looking for additional resources for your Gen Chem labs, for green chemistry resources. It's just a great teaching and learning community. We do have videos for the other equilibrium experiments. So the bromothiamyl blue one is this webinar, and the Chem A experiment 10 is a little bit older, but we have it written up. We have lots of great chemistry books and resources if you are looking for more ideas for your labs. Definitely check those out. Our books I do highly recommend because they are a site license. You purchase one and you get access to all of the experiments in their Word format to edit, photocopy, distribute as much as you want. So they're super worth it, and you get a lot of great ideas out of it that you can expand on however you like. People are always asking for a lot of videos. We have them. Check them out on our website, our YouTube channel. And we do, again, offer training. So if you still have questions about your products or how to incorporate any of this into your classroom, we have chat, we have a phone number and email, always chemistry@vernier.com. If you email that, it goes to me or my colleague Noose, who's normally here, but he's on sabbatical right now. So I'm doing it all by myself today. But definitely let us know if you have any questions or, again, feedback on this experiment. And now we are going to do a giveaway.
Yes, so we're doing a giveaway, and then there was a really good question in the chat that I want to get to as well. So I won't
Yes.
let that slip by, but
Okay.
I wanted to let you all know that I entered all of your names into a random name generator, and today's winner of either a Go Direct Flat pH or the ebook of our food chemistry experiments is Rodney S. So congratulations, Rodney. I'm going to go ahead and email you as soon as this webinar is over. So look out for an email from someone with an @vernier.com email address. If you don't see it, check your spam. And then our great question is from Kathleen in the chat. She asks, does the butterfly tea respond to temperature changes like the cobalt does?
That is a really, really good question. And it does, not in the same way. And that's when I kind of briefly mentioned it was important to brew it between 85 and 90 degrees Celsius. So that is where you brew it at would give you a different color as a result. And that's why I was like, that's another activity. But I would love to explore that activity more, that concept more. And so hopefully it makes it in there. But yeah, you can do different things with temperature with the tea as well.
And then one more.
Mhm.
Does the tea need to be made fresh for every single day that the experiment is performed, or can the tea last for up to a week and have good results still?
Very good question as well. So one tea has lots of nice, yummy nutrients in it that all kinds of microbes and bacteria love. So if you are going to store it for a while, I would recommend storing it in the fridge in a sealed container. If one night is going to be fine, but like a week, yeah, I would store it in the fridge. But your results will change over time because these are not buffered solutions. They're constantly interacting with CO2 in the air and changing over time. So you can still use that tea. It's just the exact spectra you get on Friday will not be the exact spectra you got on Monday, but the trend will be the same.
Do we have any more questions?
Yeah, what else? What other questions? Is that it? Good, good, good. All right. Yeah, if you have anything else, please contact us. Yep, we got that question. Okay.
All right, everyone. Thank you so much for joining us. And thank you so much, Melissa, for the amazing presentation. I dropped a link to a survey in the chat just now. I'm going to drop it again. Please give us feedback if you have ideas, questions, etc. We'll take a look at that later. And Rodney, keep an eye on your email. Have a great rest of your day, everyone. Thank you.
Thanks, everyone.